Welcome to this explainer. Today, we're unpacking something that sounds like it's straight out of science fiction. We're talking about the seemingly magical properties of shape memory alloys. And trust me, you'll want to stick around for this, because we're looking at a material that is actively revolutionizing aerospace engineering right as we speak. Let's dive right in. I want you to picture something. You take a piece of metal, right? You bend it completely out of shape. Crease it, mangle it, do whatever you want to it. Then, you apply a little bit of heat. And instead of just sitting there or melting, you watch as it instantly remembers its original form and snaps right back into perfect place. It totally looks like a magic trick, but I promise you it is pure material science. Section 1. The metal that remembers. To understand how this astonishing stuff actually works, we have to look back at the wildly serendipitous origin story of a material known as nitinol. Nitinol was discovered completely by accident between 1959 and 1961 over at the U.S. Naval Ordnance Laboratory. Scientists were just looking for a fatigue-resistant alloy for missile nose cones. Simple enough, right? Well, at a lab management meeting in 1961, they were passing around an accordion-folded, heavily creased sample of this new nickel-titanium alloy. Someone jokingly held a pipe lighter up to the mangled metal, and to the absolute shock of everyone in the room, the strip visibly sprang back to its perfectly straight original shape. Literally nobody expected it. Section 2, inside the phase transformation. So what is actually happening here? This magic trick is a very real physical process deep inside the metal. At a microscopic level, what we are looking at is a reversible, solid-state phase transformation. The metal is shifting between two distinct geometrical arrangements in its crystal lattice. And the craziest part is that it does this without breaking a single atomic bond. It just transitions back and forth between a tangled, easily deformable structure and a highly ordered, rigid structure. We actually have names for these two phases, martensite and austenite. When the metal is cool, it's in the martensite phase. It's flexible. You can deform it super easily. But when you heat it past a very specific transformation temperature, boom, it triggers the austenite phase. The crystal structure forces itself back into its original rigid geometry. It literally remembers its trained shape and snaps into it with an incredible amount of force. Section 3. Superelasticity, the ultimate spring. Because beyond just that heat-triggered memory, nitinol possesses a second, totally incredible superpower that engineers are heavily exploiting today. It's known as superelasticity. This is a related but entirely distinct property where the metal acts like the ultimate indestructible spring. In this state, it doesn't even need a deliberate change in temperature to snap back. You apply physical stress, it deforms by temporarily forming that flexible martensite phase, and the second you let go, it instantly springs back to its original shape. And the absolutely crucial takeaway here is this multiplier, 10 to 30 times. In its superelastic state, nitinol can bend and flex 10 to 30 times more than an ordinary metal without permanently deforming. I mean, that's just a staggering property that fundamentally changes how we design mechanical parts. Section 4, shape-shifting jet engines. And of course, engineers aren't just leaving this in the lab. They're already translating these mind-bending material science properties into massive, real-world aerospace applications. A perfect example of this is happening right now in commercial aviation. Boeing actually uses nitinol shape memory actuators on the massive GE90-115B jet engines. Those are the ones powering the Boeing 777. They use this alloy to operate variable geometry chevrons right along the back edge of the engine nozzle. And this brilliantly illustrates the practical power of shape memory alloys. See, during takeoff, the surrounding air is cooler, and these smart chevrons deflect outward automatically. This mixes the airflow and significantly reduces engine noise for the community down below. Then, as the aircraft climbs to cruising altitude and the engine conditions change, the alloy is triggered to smoothly retract the chevrons back in line. This improves fuel and aerodynamic efficiency for the long flight. And the best part? It does all of this completely autonomously. There's not a single heavy motor, servo, or complex hydraulic line involved. The metal itself is both the sensor and the actuator. Section 5. Morphing wings and rovers. Because shape-shifting engine chevrons are just the tip of the iceberg, the next frontier takes us further into the skies and all the way out to the surface of Mars. Because of that superelasticity we talked about earlier, NASA relies on nitinol wire mesh wheels for the Mars Curiosity rover. It lets the wheels flex heavily over rough, jagged Martian rocks and immediately spring back without taking permanent damage.
They're also developing this metal for self-deploying spacecraft solar sails, low-shock satellite deployment mechanisms, and advanced vibration damping systems.
Building on the massive success of those engine chevrons, NASA and Boeing have partnered on an even more ambitious vision for Earth's atmosphere. It's called the Spanwise Adaptive Wing Project, or SAW. The goal here is wild: using Nitinol torque tubes to actively fold and morph entire aircraft wings in mid-flight. The mechanics are just remarkably elegant. Engineers install these trained shape memory alloy tubes at the wing's hinge. By simply applying heat via internal electrical heaters, the metal is triggered to undergo its phase transformation. As it transforms, it twists with immense torque, effortlessly folding a 300-pound wing section over a 180-degree sweep, up 90 degrees or down 90 degrees, literally right in the middle of a flight. Section 6. The future of flight. Now, the current technical hurdle researchers have to tackle to get us there is scaling this all up. Today's components need further development to generate the absolutely massive forces required to twist a full-scale commercial airliner wing, but the technology is rapidly advancing. Which brings us to a really profound shift in how we think about aviation. As this NASA quote highlights, we are entering an era where aircraft will no longer be static, rigid metal tubes. Instead, they'll be dynamic, living machines that subtly reshape and morph parts of themselves mid-flight to constantly stay at absolute peak aerodynamic efficiency. It's a lot like how a bird naturally adjusts its feathers. As shape memory alloys completely bridge the gap between material science and aeronautics, it leaves us with a fascinating question to consider. If a simple piece of metal can remember its original shape and use that memory to safely transform an entire aircraft in midair, how long is it until every single vehicle we travel in is built with a metal that remembers? Thanks for joining me on this explainer, and keep questioning how the world around you is built.